Okay, Prof. Zaher and everyone, it is time to start our lecture. I will open first. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Our honorable guest lecturer, Associate Professor Zaher Judeh from Nanyang Technological University in Singapore, Head of Department of Chemistry, Head of Undergraduate Program, Department of Chemistry, Dr. Muhammad Ridwan, all faculty staffs at the Department of Chemistry. Today, I see some lecturer also join this lecture series. Welcome, Dr. Tuti Wukirsari from Biochemistry Division, and also other researchers. Our students in synthetic organic chemistry, our students in the research laboratory, and also all participants. Today is the second meeting of the organic chemistry lecture series held by Department of Chemistry Universitas Indonesia with full support from International Office University of Indonesia. And in this lecture series, we have a prominent speaker from top university, Associate Professor Zaher Judeh from NTU. Specifically, this is held in conjunction with the synthetic organic chemistry class students. So I have divided the SKOA students into 10 groups. So each group is required to actively participate in this lecture series by asking one question, and please note the question and also answer and discussion with Professor Zaher. So the material will be very important, very beneficial for you for facing the test, especially, and also to improve our knowledge about organic chemistry in general. So for this meeting, we have two parts. The first one, the Professor Zaher will deliver the material, the presentation, and after that, the synthetic organic students will ask their question. So in each group must be one of a member ask the question, and then other student note the answer and discussion until group 10. We have still time. Prof. Zaher also have a question for you. So please actively participate in this organic chemistry lecture series. So without further ado, this time I give to Professor Zaher to deliver his lecture. Professor Zaher, the time now is yours.
Thank you so much, Professor Bayu. Thank you so much. Assalamualaikum. I would also like to thank the head of the department and Professor Ridwan and all of you guys that attended, and all the lecturers and the professors listening to me this afternoon. I think it's good to have a good discussion. And if the students ask me a difficult question, I only have to transfer it from one group to another group. So I don't have to answer any question. So that's what I will do. Let me start from where I stopped in last week. So this is a summary of the first section of what we have discussed last week. And last week we said carbohydrates. So if we have carbohydrates, they react with these type of nitriles in the presence of a source of a nitrogen to give us this pyrrole type of compounds. And we said that this is a simple reaction. It's a one-pot, three-component reaction. It is using a simple catalyst, triethylamine, to give us the product. For chemistry students, especially at the undergraduate level, you can really appreciate that this reaction is what we call a cascade mechanism, and it involves Knoven-Gillen condensation, oxomichael addition reaction, Thorpe-Ziegler type reaction, and then ring opening aromatization. So there are a lot of mechanisms that are happening just in one step of this reaction. So this is what we have discussed last week. And if you guys remember last week, I asked you, how do you make compound 1 and compound 2? So we had a discussion, and some of you have correctly answered these questions, right? So some of you said that, what we do first, we take the same reaction that we have discussed last week. You take a carbohydrate reacted with a nitrile in the presence of ammonium acetate to give us the usual product. And then what we do a simple alkylation to alkylate this nitrogen here to give us the product. That's what you asked. That's what you answered. And this is really correct. All right. However, if our process of alkylation does not work to make these type of compounds, because how do I make this chemistry happening at this stage, right? So it's not possible. Therefore, to make some sort of a direct link between nitrogen and the aromatic moiety is very difficult through this process, all right? So this is one thing. Another thing to notice here is the following, that if I want to make my targeted product, I need to have 2 steps. For us, we talk about sustainability. We are talking about doing simple chemistry. Therefore, the lower the number of steps in any reaction, the better the chemistry is. And this is what we have tried in our research. So our previous lecture spoke about the preparation of unprotected nitrogen. Today, I'm going to talk to you about how do we make these compounds in just one step. All right? So this is the summary of today's lecture. I'm going to take my carbohydrate, I'm going to take an active methylene compound, and I'm going to convert it to my targeted products here in presence of these types of amine. So I have here now what we call N-substituted type of pyrrole. These are important type of compounds. The objective is to make these compounds in just one step. So what we did in the beginning is the following. I want to take you back to what we did before. So in this kind of chemistry, our reaction conditions are mentioned here. All right. So this is for our students who are really thinking about, so how do we start research? How do we start reaction? What do we do? What are the conditions that we need to adapt in this kind of work? So for us, because we are very familiar with this reaction, these are the optimum condition. It makes logic that we start our chemistry using these conditions. So we just took a glucose and we took the nitrile, and instead of taking ammonium acetate, we took this type of amine. Under the same conditions, the optimum condition that we have developed previously, which are mentioned here, then we found that this reaction gives us a 20% yield of this kind of pyrrole. Yes, the reaction is happening. However, it's not what we are used to. What we are used to obtain is 2, 3, and 5 substituted pyrrole. This time, we are obtaining 2, 3, and 4 substituted pyrrole. Then we tried to change the solvent, and different result. We obtain different results. We obtain mixtures of product. This is a complex mixture. Because of our experience in this work, we somehow inferred that this mixture contained also 1A. Therefore, the next step was for us to try and find what are the optimum reaction conditions that we use to obtain both A and 1A dash. And this is what we did. So we screened different types of catalysts, including acids and bases, as you can see here. So we took acetic acid, triethylamine, tetrabutyl ammonium bromide, tetrabutyl ammonium fluoride, and this is sodium ethoxide, sodium acetate, sorry. And this is para-toluene sulfonic acid. This is camphor sulfonic acid, tetrabutyl ammonium hydrogen sulfate. Right, we keep the reaction condition, the solvent the same, the temperature is the same, and here are the yields that we obtained. So some of these catalysts gave us mixtures of products, some of us gave us purely 1A dash, and again this is a mixture, and this type of catalyst, tetrabutyl ammonium hydrogen sulfate, give us 100% 1A. However, the yield was really very low. So the next step we wanted to do is to optimize the yield of this reaction using this catalyst, because this catalyst give us 100% selectivity. We noticed that no, this is a ketone. This is also an aldehyde. The amine can either react with the ketone, also the amine can react with the aldehyde. That is what we noticed. So we thought that we can try the reaction by mixing everything together or by doing the reaction in a sequence. So if you do this reaction and mix everything together using the same catalyst in DMF or ethanol at 80 or 60, again, you will get 100% selectivity here and here, but you get mixture of products here once you reduce the temperature. So reduction of temperature give us mixture of products. However, the yield of the reaction increased. We thought that we should do the reaction in sequence. We have two sequences, sequence 1 and sequence 2. In sequence 1, what we did, we mixed compound 2 and compound 3 together. We mixed these two for about 2 hours so that the intermediate is formed. And after 2 hours, we added the glucose. This gave us 60% yield of 1A in 100% selectivity. If we follow sequence 2, in which we take the glucose and we take the amine, we mix them together, and then the reaction continued for 2 hours. After 2 hours, we add the nitrile, then this gives us 45% yield and mixtures of product. After optimizing the reaction for the number of moles for the catalyst, we found that number 13 is the optimum reaction condition. So the reaction is done based on sequence 1 using solvent ethanol, 60 degrees. Our yield is 58% and 100% selectivity. So this is the optimum reaction condition that we managed to develop for this reaction. This reaction condition here give us 1A selectively. All right. We wanted to understand if these reaction condition are also good for other types of carbohydrates and other types of amines or nitriles, and therefore we had to look and study the scope of the reaction. So taking different types of carbohydrates like a glucose, ribose, and rhamnose, different types of nitriles, different types of amines, this reacted to give us the required or the desired product in 50 to 73% yield. All right. For example, the reaction with the glucose, you can see this type of the amine here, long chain amine here, hydroxyamine here, an amine with a double bond here, and you can have an aromatic primary amine. You can have again an aromatic amine. You have cyclic amine, cyclohexane. So this is coming from aniline. Remember what I was talking to you about? This one also coming from aniline as the source of amine. So this doesn't have any substituent. It has a methyl substituent on the para position. It has a methoxy substituent on the meta position. All of these amines worked very well to give us very high yield of the compounds. I want you to note a little bit that the reactions with anilines are give us a little bit lower yield than the reaction with primary amine. Well, this is really expected because of the reactivity of these compounds. So this slide shows us the reaction of different amines with the glucose to give us the desired compounds in high yield. This slide here shows us the same reaction, but here I am using ribose as my sugar, and I'm using basically the same amines and the same nitrile. This reaction proceeds very well to give us the product in about 50 to 73% yield. You can again see here that this is our nitrile, this is our aniline here, and here the reaction gives us the product in very good yields. Not only glucose and ribose react, but also rhamnose react to give us the same type of Pyrroles in excellent yields. Again, here is our aniline is shown here. So this is just to depict the versatility of this reaction, whether we are using aromatic, we are using aliphatic, or we are using amines that has double bond here, or aromatic ring, as you can see here. All of these reactions are really successful and give us the desired product as needed. Does anybody have any question about the things that I've discussed so far? Please let me know if you have any question. I'm happy to answer. Otherwise, you can note the number or page and we can come back to it later. All right, so this slide shows us the optimization and the scope of the reaction as for 1A. Next, I'm going to discuss the optimization and the scope of reaction for 1A dash and how we obtained this. So in case of 1A dash, we know that sequence plays an important role in this reaction. And we know from previous results that sequence 2 is the one that best gives us the product in high yield and also high selectivity. Therefore, we adapted sequence 2, as you can see here, and we screened different types of bases and also acids. We found that depending upon the catalyst that you use, the best results are obtained when acetic acid is used as the catalyst in this reaction. And for this case, the selectivity we obtain is about 94% selective towards our desired product, which is 1A dash. And the yield for this is 57%, right? Then because of this, from these results, we took this acetic acid and we tried to actually optimize more for this reaction. And here is what we did. So here is the result from the previous slide. And again, so we wanted to understand if at optimum reaction condition with acetic acid, does the yield change if we do the reaction in which we mix everything together, or we even use sequence 1? And indeed, we found that the best result is still using sequence 2, and here is the ratio. We wanted also to reduce the number of moles of catalyst that we use from 1 to 0.5, and this reduction in the number of moles have given us basically similar or slightly better yield, 59%, and the selectivity remained the same. So number 10 is the condition, the optimum condition for obtaining product 1A dash. And this is the condition that we have used to examine the scope of this reaction. It is really important to understand the difference between 1A and 1A dash, which is the substitution pattern here at the ring here. So different Pyrroles have different substitution pattern. Therefore, it is critical to actually obtain this in our reaction. So looking at the scope of the reaction, again, we use these types of carbohydrates to react with the nitrile in presence of different types of amine to give us our Pyrrole here, which is 2, 3, and 4 substituted Pyrrole. So from glucose here, we are able to obtain the simple type of Pyrrole in which we have a methyl group here, a long chain here, with a double bond here, with an aromatic primary amine here, with 2 carbons separating the aromatic ring from the nitrogen, 1 carbon separating them, a branch amine, as you can see here. All of this worked very well to give us the product in very good yields. Looking at the reaction with ribose, again, ribose reacted with these amines here and here and here, here and here to give us the product in very good yield. The reaction happens again with rhamnose. As you can see, we have only given here 4 examples to demonstrate the concept of this reaction. And also the reaction happens with disaccharides, as you can see here, with slightly a bit lower yield, 53% here with maltose, 45% again with maltose, long chain, and cyclic cyclohexanamine. All right. One thing that we could not really obtain in this type of reaction is reaction with anilines. So we could not obtain any reaction with aniline in this. Every time we do this reaction, we obtained no product. We still don't understand why. We have tried different conditions, but we could not really obtain this reaction here. So we are still trying. We'll see how it goes. All right. One of the things that gave us a problem initially, if you look at these structures here, if you look at this structure here, the only difference is the substitution pattern. All right. To differentiate which one is which by NMR, it was very difficult. So the only the critical signal that we are looking at is this proton here, and there's another proton here. So these 2 hydrogens are the one that differentiate between the 2 structures here. However, if you look at the NMR of these, you will find this is the signal for the proton here, and this is the signal for the proton here. All right. So these 2 have the value at 5.12 and 5.21. These are very, very close to see which one is which we did an extensive 2D NMR to differentiate between the two. And based on the NMR, we were able to actually assign that this NMR belonged to this structure and this NMR belonged to this structure based on 2D NMR. However, we were very lucky to obtain a crystal structure of both the different 1A and 1A dash. And these crystal structures, they corresponded to our NMR conclusion. And this proton here is actually this proton here. And this proton that we get here is this proton here. So X-ray helped us to confirm the structures. All right. So now looking at the mechanism of this reaction, what we try to do is to try to study the mechanism using mass spectroscopy. In the previous work also, I have shown you the mass spectroscopy and how we concluded the mechanism of the reaction. Here we also found that mass spectroscopy is really very useful for us. So we did the reaction at different type of intervals, and then we looked at the mass spectroscopy of this. So how we did the reaction? So we started our reaction. We took the first sample. After each 20 minutes, we start taking samples and then injected in the mass spectroscopy, and we look for signals or peaks that correspond to our intermediates. So based on our experience with the mechanism from the first section, this reaction proceeded as follows. The mechanism for 1A, so I'm going to talk about the mechanism for 1A and then later for 1A dash. So for 1A, remember that the sequence involved the reaction between the nitrile and the amine first. So the reaction of these two reactions here involves a nucleophile electrophile reaction. You get this Schiff base. The Schiff base tautomerizes to give us intermediate 2. Now, intermediate 2 reacts with our carbohydrate. So you're pushing the electrons here, and this double bond react here, becomes a nucleophile. It reacts on this carbon, kicking out electrons and oxygen, and you get intermediate 3. In intermediate 3, this proton here, which is next to the nitrile, is very acidic proton. So it can easily be removed by a base, in which these electrons will come here, and this will shift to neutralize the nitrogen here, and this will give us our intermediate 4. In intermediate 4, we lose water, eliminate water to give us intermediate 5. Now, intermediate 5 undergoes ketolization to form the keto form. So this is our enol form, right? And this is our keto form. Keto form undergoes reaction in which nitrogen attack this electrophilic carbon, kicking out electrons and the oxygen to give us this intermediate. Now, you recognize that this ring here loses water to give us a double bond here so that it becomes aromatic. And from your first year chemistry, you know that aromatization is a stabilizing factor. And the driving force for this reaction is the formation of pyrrole, which is aromatic, right? So we were able to observe intermediate 1 and intermediate 2 in this mass spectroscopy. So intermediate 1 here and intermediate 2 here. Okay, so this is our proposed mechanism for formation of product A, which is really, as if you look at it, it's simple. It just involves movement of electrons and then loss of water. In case of mechanism for 1A dash, this reaction proceeds as follows. So this is sequence 2. Sequence 2 means the following, that we are reacting the carbohydrate together with the amine in the first step. Again, the reaction is the same, nucleophile, electrophile. to form this Schiff base. So this is our intermediate, and then our Schiff base diatomerizes to form the keto form. Here's our keto form. The next step is that a nucleophile react with the electrophilic carbon here to give us our intermediate 3. Intermediate 3 loses water, so we have dehydration here, and it gives us this double bond here. The next step here is the following. Electrons move here. These electrons attack the electrophilic carbon, while these electrons in the double bond moves on top of the oxygen to give us intermediate 5. As seen before, this intermediate 5 loses water, dehydration, to form our product, which is again aromatic. So this is the mechanism that we have obtained here, and this mechanism are kind of the idea came from supported by mass spectroscopy. All right, to summarize this section, what we did is the following. So we took different types of carbohydrate in the presence of nitriles, in the presence of amines. This could be alkylamine, or it could be an arylamine. And by using 2 different sequences, we are able to obtain 2, 3, and 5 substituted pyrrole, or 2, 3, and 4 substituted pyrrole in good to excellent yields. This is what we have obtained, or this is what we have achieved in this section. Right. Maybe we can kind of stop here and see if the students have any questions regarding this section. And before I start the next section, are there any questions that the groups want to ask regarding this section?
Okay, maybe a question from Christy. Please mention which group, and please your question.
Okay, hello, sir. My name is Christy from Group 1. Okay, I'm really curious about this reaction 1A acid. That the catalyst of the acetic acid is the best catalyst, the resulting the greatest yield, isn't it? But my question is, but why the 0.5 mole has slightly better in yield? As we know that the more concentration that we give supposed to give the best or the greatest result. Thank you, sir.
So we are talking about this one here, right? Am I correct, Christy?
Yes, in the slide, sir.
Okay. So I just want to correct your information. It doesn't mean that higher catalyst always give us higher yield. It doesn't mean that. Yep, not always. Sometimes with higher, sometimes the catalyst is involved in a reaction. It catalyzes side products, and it really reduces the yield. So sometimes what we need to do is we actually need to reduce the catalyst so that we are able to obtain higher yield. I don't know in our case what is really happening, but the yield, as you can see here, is, I believe you are talking about this one. You mentioned acetic acid, so this one is not acetic acid, but the concept is the same. So here, what we are talking about here is that lower catalyst give us better yield, and I think we are able to prevent side reactions from happening. That's probably what we are able to do in this type of chemistry. So lower yield give us better, lower catalyst give us better yield. So I think we are able to prevent side reactions, because you know that carbohydrates are really the side reactions in carbohydrate chemistry is a lot. So preventing them and ability to obtain higher yields is not so easy. But we are very lucky to obtain really good yields from these simple reactions, especially we are using unprotected carbohydrates.
Okay, thank you so much, sir, for your comprehensive answer.
Thank you.
And there is a question again from Puan.
So, Christy, I think you are referring to this slide. So I got what this is the slide you are referring to, but the concept is the same. Yeah, this slide or that slide is basically the same concept. So I want to also highlight what we are talking about here. So listen, we are here doing reactions on using a small scale. All right. When you are dealing with a small scale, a little bit of material that is lost during purification or during transfer of material from one flask to another flask can affect your yield very, very much. This is one thing. Another thing is this. Sometimes if your product is not 100% pure or it is not 100% dry, then the yield will tend to be a little bit more. For me, I don't see a difference between 57% and 59%. This could be in this reaction here. When we did this reaction here, maybe our product was not 100% pure, maybe not 100% dry, or maybe in this case here, when we did this reaction with 0.5, maybe we are able to actually transfer everything from the flask so that we are able to calculate the yield. Maybe in number 7 here, maybe we have just lost a little bit while we are transferring. So in short, there is no big difference between 57 and 59 if you are doing reaction in very small scale, right?
Puan, you want to ask questions?
Group 1, do you have any more questions?
We couldn't hear you.
Can you hear now?
Now it's okay. Okay, mention your group.
Okay, thank you so much for Prof. Zaher, Mr. Bayo, and all of the participants. My name is Puan Hazali Putri from Group 4. I want to ask, actually, my question is quite similar with Christy. It's from slide 36. Yes. So you said earlier that the optimum reaction is actually number 13. But if we see here, number 11 actually gave a greater yield than number 13. So why you choose number 13 as the optimum reaction? That's my question, sir. Thank you.
Right. So we chose that 13 is an optimum reaction condition because in number 11, we are using 1 mole. Here, we are using 0.5 mole. All right. And if you look here, the difference between the yield 60 and 58 is not big difference. As I explained, you know, this is something that a difference of 2% is not a huge difference. So what would you choose better? To have almost 50% lower catalyst or to have a 2% increase in the yield? All right. This increase in the yield between 58 and 60 may not be really true, right? Because as I said before, it just could be a matter of percent purity. It could be that this is more pure. It could be here that I just had a little bit of water or moisture. It could be that in this case, I transfer everything in the flask. In this case, maybe I just lost some material while I was doing transfer, right? If you tell me that, okay, 47 and 58, I will tell you, yeah, this is, a huge difference. This is a big difference. But between 60 and 58, there's not really major difference here. So that's why we chose 13 as, the optimum reaction condition, because, have 50% reduction in the catalyst. 50% reduction means a lot. It's not just only the cost of the catalyst. It's not only the material that we need, because you also, if you are doing an industrial process, on addition of the cost that you use, you also have to have a purification, right? You need to purify the product from the catalyst. You also have to dispose your catalyst. So reduction, 50% reduction means a lot of saving, a lot of control over the processing of the reaction at industrial scale. Is that does that answer your question?
Yes, sir. Thank you so much for your question, for your answer.
Thank you.
Okay, maybe one question for this section. Abdul Rashid, you want to?
Yes. Assalamualaikum, Mr. Professor. My name is Abdul Rashid. And I would like to ask a question about the different treatments you did. Can you explain why do we get different outcome if we do the reaction in sequences instead of doing it all at once?
Right.
That's all from me. Thank you.
Yeah. So as I said, so in the slide here, sequence means that you have to do the reaction based on starting with materials and then doing the reaction for some time. And then once the reaction is completed, you add the other material. So if you follow here for sequence 1, for example, let's look at sequence 1. Sequence 1 involves the following. I am taking these two and reacting them together. So the reaction between these two forms a Schiff base. And if you remember my mechanism, then this is our intermediate that allows the reaction of a glucose to add to it. So in the beginning, we have 2 and 3. We mix them together to form the intermediate. We must first form the intermediate, and this reaction takes place in about 2 hours. So we heat this one for 2 hours to give us the intermediate. We follow this reaction by TLC to ensure that there is no starting material of the nitrile or the amine. So once they disappear from TLC, it means the intermediate is formed. Why do we need to do this? We need to do this to prevent the reaction between our amine 3 and the glucose, so that the other product is not formed, right? So in sequence 1, these are formed, and then glucose is added. And this is shown to us in the mechanism. So these two react together. This is the intermediate that we are talking about. So once this intermediate is formed, which here is tautomerizes, this glucose react with the intermediate. If we don't completely form the intermediate, glucose can also react with the amine to give us mixtures, but we don't want mixtures. So this is the sequence 1. In case of sequence 2, maybe you can look at this one here. So in case of sequence 2, what we do, we take the glucose and we take the amine and react them together to form an intermediate. Again, this reaction takes place 2 hours. Again, we follow this by TLC. So once this intermediate is formed between 1 and 3, then we add our nitrile to the intermediate to complete the reaction. Again, this is shown to us in this mechanism here. So we take 1 and we take a 3 to form this intermediate. All right. This intermediate reacts with the nitrile, and the product is obtained. Abdul Rashid, is that does that satisfy your question?
Yes, Professor. Thank you for your answer.
Thank you. How about group 7? Do you have any question, or group 8? Any questions from a group 7 or a group 8? Dr. Bayo, this group listen to you, they don't listen to me.
Yeah. Group 7, all right. Do you have question? So far, group 1, group 4, and group 10 had already asked their questions and also note the answer. So other groups, you want to ask questions from this section? Oh yeah, Muhammad Fidrio first. Okay.
All right. Thank you for the opportunity. Hello, Prof. Zaher. I'm Muhammad Ibrio from Group 5. I want to ask a question. Yesterday, you said that the triethylamine is react in the reaction, right, from hydrogen bonding. I want to ask if today reaction with the solvent and with the catalyst, is there any reaction that occur that control the yield? So can it lowest the yield or highest the yield from the reaction from catalyst, then can go away? Thank you.
Thank you, Muhammad. I think you have a good memory, Mr. Muhammad. So yes, triethylamine is still, so in the last lecture, what I said triethylamine does make hydrogen bonding with the product. So these products, for example, if we look at this product here, if our catalyst is triethylamine, there is hydrogen bonding between our triethylamine and the OH groups here and here and here. All right, we still have this hydrogen bonding, and we use the same process of purification that I explained last week. So yes, we still have hydrogen bonding, and triethylamine is still stuck there. But based on our experience that we developed from the previous reaction, we are able to solve this issue without any problem from this reaction. So yes, you're right.
So that doesn't affect the yield from the product, Professor?
The yield, so there is no effect on the yield. There's no effect on the yield. I don't think there's effect on the yield. We have, after some time, when you develop more experience in reactions and you are able to overcome the problems, so you become an expert in this reaction. So what we do, so before we do the column chromatography, we take a little bit of a triethylamine and we flush the column with the triethylamine so that we saturate the OH groups, the acidic groups on silica with the triethylamine. Once we saturate, then we are able to do the column easily. So triethylamine will get stuck on the silica also. So yeah, we have that experience right now.
Thank you for the answer.
Next, Kevin.
The next question is from.
Hello, I'm Kevin from Group 2. I want to ask, beside the factor on the table in ADAS optimization reaction, are there any other factor that can affect the yield, like pressure or longer reaction time?
Oh, right. Okay. Thank you, Kevin. So pressure, I don't think this pressure affect the reaction, and we have not tried to investigate the pressure, but reaction time certainly does. Yeah. So remember that these reactions are done at a specific temperature. All right, and this temperature here we are using 60 degrees. All right. This reaction is done about we do this reaction for 6 hours. So imagine that you leave the reaction for a longer time. Okay, we found that the yield decreases over a longer period of time. Therefore, it is important for us to optimize the reaction time, right? Especially if you do the reaction at higher temperature, 80 or 100 degrees. Yes, time really makes a big difference. And you can observe this visually, Kevin. So if you do the reaction, over time, as you increase the reaction time, the reaction becomes really dark, really black. Yeah. It is good to have the reaction a little bit dark yellowish to a little bit blackish, it's fine. But if reaction goes very dark, then you know that the reaction has decomposed and there are no products there. So yes, color is a good visualization for us to obtain. And we must control the reaction time. It's a very critical point here. Kevin, is that, do you have any other question?
No, thank you.
All right, thank you. I can see Vanessa.
Hello, Professor. My name is Vanessa from Group 9. I would like to ask about why do each solutions or mixture need a different time to stir? There is one solution that needs 6 hours to stir, and there's 4 hours. There's the other one that needs 4 hours to stir. Like, what could be the factor of it? Thank you.
Vanessa, can you please repeat the question slowly so I can understand?
Yeah.
Yes.
Okay. Why do each solutions or mixture need a different time to stir?
Oh, okay. So each solution or mixture has a specific time for reaction. So if you look at, so first of all, these two reactions, whether we are using sequence 1 or sequence 2, the reaction time is 6 hours. Both of them, the reaction time is 6 hours. However, in order for us to do the reaction, we do it in a sequence. What is the sequence? For example, I am mixing these two together first, and I need 2 hours for these two to completely react. The way I know that is just figuring out the TLC. All right. These two react, it just needs 2 hours, yeah? Depending upon their reactivity, they need just 2 hours to give me the intermediate. However, this intermediate, when it reacts with my glucose, it needs about 4 hours for the reaction to complete. That depends upon the reactivity of the glucose with the intermediate. So reaction energies, you need to have the proper time for reactions to be completed, and you observe that by TLC. Does that answer your question, Vanessa?
Yes, thank you very much, sir.
Okay.
Vanessa, TLC is thin layer chromatography. So maybe you has not already know how to do, but slowly you can study maybe in next semester if you take chromatography course.
So
Okay.
let me explain a little bit what Professor Bayo has said.
Ah.
So thin layer chromatography is, from the name, it's a thin. So this is very thin. It's a layer, and we use a chromatography. So thin layer chromatography is a very good, very good test for us to understand if the reaction is completed or not. So we draw a line here, and we have two samples. Here is our starting material, and here is our product. Okay, when you do this type of experiment, you take the thin layer, the TLC here, you take it and dip it in a solvent. Yeah, you dip this one in a solvent. Okay, and then this solvent will go up, capillary, osmosis, whatever, and then this solvent will mix with the spots here and push the spots up. These spots are pushed up based on their polarity. Less polar goes higher. More polar goes down. Very, very high polar goes even here or even doesn't move. So when you are comparing the the reaction, when you are doing testing the reaction, what you do, for example, let's say that we are reacting 2 and 3. All right. When these two react, what you do, you take the product and you spot it here. So this is product. And now you want to see if the starting materials have reacted or no. So you take the starting material and you spot it here. You take the other starting material and you spot it here. All right. So this is 2 and this is 3. And then you develop this in the solvent. You will find that, hey, this one maybe is here. And you will find this one maybe is here. And you will find this one maybe it's going to be here. All right. Okay. The reaction is indicated to be complete if I don't observe any corresponding spots here. Means that the reaction product does not have a starting material here or here. If I don't have these spots here, if I only have one spot, that means my starting material has completely converted to the product because I don't see it in the reaction mixture. That's just a little bit of the TLC that we are talking about. Any more questions?
No, that's clear enough, Professor.
Thank you.
Thank you.
Professor Zaher, do you have a second section of your material?
Yes, we have another section. Just depends upon you. You want to go for a break or?
Okay. We have already half of the group asked their questions. So I think please go next, and then we can have more discussion after the section 2.
Sure. We can do that because I want the groups also to ask more questions in the next half.
Yes.
Yeah. So please make sure you prepare your questions. Okay. All right. So in this type, so the summary of this work, as you can see here, I'm able to make these type of compounds, right? All right. What is these types of compounds? If you note that this and this are one, usually it is an alkyl group or aromatic ring, right? It is either alkyl group or aromatic ring, as you can see here. Okay. Now, when we were doing this kind of chemistry, and some of the reviewers ask us, hey, why can't you change a phenyl group or a methyl group to something different? Because there are some structures that have interesting kind of arrangement here. So this is what we are going to talk about. Here, I am changing the methyl and the phenyl group into this group. All right? This is the topic of this work here. So what I'm doing here, I am taking the carbohydrates, the active methylene compounds, I'm taking amine, and I'm making these types of compounds. Instead of this and here and here, I am making this type of compounds because these type of compounds are very, very important. Why are they important? Because first of all, these type of compounds are called 2-amino 3-cyano-pyrrole. This is our 1, this is 2, and this is 3. So 2-amino 3-cyano and pyrrole. This is a very critical kind of arrangement, 2-3, because you can make a huge number of rings from here. Example of the rings and example of the structures I can make utilizing these two groups are mentioned to us here and here and here and here. Likewise, you have it here. You also have it here. You have here, and you also have here. This on the left side, these are basically drug molecules, and on the right side, these are intermediates that are used as lead compounds which have very high bioactivity. So it seems that in the literature, this type of starting material or intermediate is really required and is really important. Therefore, the next few slides will talk about this, obtaining this material using our chemistry to satisfy the need in the literature. How did we do this? As follows. First of all, in the literature, there's a report that was published in 1986 to make this type of compounds. And this report used the following. First of all, this is a two-step reaction. First of all, you need to make this intermediate and then react it with the malonitrile to give this product. All right? So you have a two-step reaction. The first, you need to make this and then react it to make the product. Okay. This chemistry too is not new to us. If you remember, I spoke to you in the beginning about formation of pyrroles. In pyrroles, what we did, we took carbohydrates, malonitrile, and then we obtained this type of pyrrole. So this is something that we have experience in. All we need is to translate our chemistry not to form furans, but to form pyrrole. This is how we did this type of chemistry. So we took the carbohydrate, we took the malonitrile, and we took the amine, and we are able to obtain this product. 1, 2, and 3 substitution, and this is the arrangement that we need, 2, 3. This reaction also, we found that it can give us this furan under some condition. We have tested different types of catalysts. We have used either reactions together or using sequence 1 or sequence 2. Ethanol was the best solvent for this. And these are the reaction times. All right. If we are using sequence, therefore, if you're using sequence 1, we take 1 and 3. This is our 1. This is 3. We mix them together for 2 hours first, and then we add substrate 2 and continue the reaction for 1 more hour. If we're using sequence 2, what we do, we take starting materials 1 and 2, mix them together for 2 hours, and then we add a 3 and we continue the reaction for another 1 hour. So here, this reaction is completed in just 3 hours. As you can see here, acetic acid gave us the best kind of yield, all right, and selectivity, all right. Here, for those who ask me about, which one is the optimum catalyst, I am using here 1%. The reaction time is 2 hours. The yield is 70, and I'm giving 100%. I'm getting 100% selectivity. If you compare here, I'm using here 50% less catalyst. However, here the reaction time is higher, and I have an impurity here. My impurity here is this furan. So for me, which kind of catalyst I prefer? Which kind of condition I prefer? Do I prefer condition 10 or prefer condition 12? No, in fact, I prefer condition 10 because it gives me selectively the product. All right. The difference between the yield is not much. This is 70 and that one is 72, and the reaction time is even less. Therefore, number 10 is the optimum reaction condition. Okay. So after developing this reaction condition, we wanted to understand if this reaction is general, and if I can continue the reaction using different types of amines, different types of maybe nitriles, different types of carbohydrates. So what I did here is this. I took different types of carbohydrate, hexoses, pentoses, and even disaccharides, malonitrile, different types of amines, and using the same type of catalyst to give me the product. If you notice that this reaction is done in 2 steps, actually the reaction require 1 step, all right? And the first step gives me the OH, all right? But what we found, it was really difficult for us to separate the compound if it is OH and OH because of the polarity of the compound, all right? Because of the polarity of the compound. So in order for us to reduce the polarity and get the pure products through chromatographic separation, what we did an acetylation step. So after this reaction is completed, so when I do the reaction, all I need to do is add acetic anhydride in the presence of DMAP and in dichloromethane. This gives me the acetylated product in which all the OH groups here and here and here and here, all of them get acetylated. All right. And after I get the groups acetylated, I'm able to separate it easily because it is not very highly polar compound. This is a trick that we adapt to solve problems that are involving purification because of high polarity. What we do, we break down the hydrogen bonding by, for example, acetylating the product. So if you look at this, slide here, I'm using here different types of amines, and here, all the way here, and different types of amines, right? Okay, and in all cases, the product is formed really in a very good yield. In this slide here, I'm using this type of carbohydrate, and here I am using disaccharides. I'm using disaccharides to give me the product. So what we can conclude from here is that, hexoses works very well, pentoses works very well, and disaccharide works very will to give us the products, right? Okay, this reaction also is done on large scale. And if you notice here, because we did the reaction on 2 gram, and again 2 gram here, this is done on 4 gram, even higher scale. And in all cases, we are able to obtain excellent yield of the product, although here is a little bit to the lower side. What you notice here is that we left these products as the hydroxy or the OH products. We did not do acetylation because this is large scale and we are able to easily purify the product because it's large scale. Previously, we are dealing with milligrams. The product is so little, therefore we have to do acetylation in order to do the purification. All right. Nevertheless, what I want to say here, that this reaction is working on large scale to give us the products, as you can see here. It means that this reaction can be scaled up without much problems. All right. This also can be modified. The structure also can be modified. The aminocyanopyrrole can be modified easily. For example, this group here can be converted to an aldehyde group here, and this group here can be derivatized here and here. All right, so we can make derivatives of these groups, and this shows the diversity and ability to transform the starting material into different products. Here is just the X-ray structure of the 4-mil pyrrole. All right, coming to the mechanism of this reaction. This reaction is really interesting. The mechanism is also very simple, and it builds us on our previous work. All right, so I'm showing the mechanism here with an octyl amine. So this is our amine. All right, this reacts here, kick out electrons here, and this is the intermediate that we get. Okay, this intermediate tautomerizes here, so this electrons shift here, and I will get this intermediate. Next, this is the enol form, and the enol form is converted to the keto form, and this is called the open chain Amadori product. All right, this is discovered by Professor Amadori, and we call it the Amadori product. Now, Amadori product can be in a form of open chain or a close to form ring. So here is the ring of the Amadori product. How do we obtain the ring product? This reacts here to close the ring, and you get this bond here. All right. So Amadori product, both the open chain and the closed chain, or the ring Amadori product, are interconvertible, and they are present in an equilibrium. Let's just highlight our mechanism using the Amadori open chain product. This is our nucleophile. This reacts on the carbonyl group here to kick out electrons here to give us this intermediate. Now, this intermediate is very reactive. The nucleophile react on the electrophilic carbon, kicking out electrons on the nitrogen, and we get intermediate 5. All right. Base takes this proton. Base takes the proton, electrons move here, kicking out electrons here, and these electrons move to pick up a proton, as you can see here. The result of this reaction is the formation of the pyrrole, the required pyrrole, which is shown to you here, which is an aromatic. Okay, now we have done a lot of NMR to figure out the mechanism of this reaction. So we have followed the reaction using NMR. How did we do that? As follows. We mix the starting material. The starting material is our glucose and octylamine. And after we mix them, we took sample. So this is a 0 minute. We took sample after each 20 minutes, then 40, then 60, and continue all the way till 2 hours. All right. In the 0 minute, in the beginning of when we mixed the glucose and octylamine, what we can see the glucose, we can see the octylamine, and we can see acetic acid. In fact, what we see here is both the anomers of the glucose, the alpha anomer, as well as the beta anomer. The alpha anomer is this signal is coming from the alpha anomer, and this signal is coming from the beta anomer. As the reaction continues, or as the reaction starts, you can see there is a decrease in these signals. So these protons here, this proton here and here, their concentration decrease. It means these two products are reacting. You can see here, decrease, decrease, and basically here, I don't have much. I have a little bit here, if you can see it here. All right, that tells me that this reaction here completes in 1 hour. All right, so this is another way to check if the reaction has completed or no on top of TLC. We can use NMR. Now, once this reaction complete, we add the malononitrile. Remember, this is our malononitrile. We add it to the reaction mixture, and then we follow the progress of the reaction. The minute we add malononitrile, we can observe signals here and here. These signals are coming from this proton here and this proton here. This is proton 2, proton 3. As the reaction progresses, these signals becoming more concentrated, and these signals even more concentrated at the end of the reaction. You can see this is a well-formed product, and it's considered as clean product. All right, there are no starting materials in this reaction. Right, so this is how we discovered, or this is how we proposed the mechanism of the reaction based on this NMR study. And then in the NMR also, we found that we are able to obtain Amadori product, and we are able to characterize Amadori product by proton NMR as well as C13 and DIP. All right, we are able to assign the different carbons to the structure here. Amadori product is this one here. All right, this one here. Okay, it's here. So we can characterize that from our NMR, as you can see. Okay, we also did mass spectroscopy to complement our NMR study, and we can find in the NMR studies in the beginning when we mix the glucose and octylamine, we can find intermediates 1, 2, 3, and 4. Now, when we add our malononitrile, these intermediates, they decrease and the product start forming. All right, the product start forming. They decrease, more product, they decrease, and more product. Okay. All right, so to summarize this work, this is what we have. We take carbohydrates, we take malononitrile, and we take an amine. We do the reaction using a catalyst, which is acetic acid, ethanol, 60 degrees, and we obtain our 2,3 product, as you can see here. 2-amino, 3-cyano-pyrrole. The yields we get in this reaction is 58 to 86% yield. This reaction works on large scale, and the mechanism is supported by our NMR and LCMS experiments. I think I can stop here for more questions. Does anybody have any question? Does the group have questions?
Okay, anybody have questions, especially for group 3, group 6, group 7 and 8?
Does anybody have any question? Any group has any question?
Very basic question is also acceptable, so don't worry.
Any question is acceptable.
Yeah, it's acceptable. Okay, please, Ahmad.
Yes. Hello, sir. First of all, I want to say thank you very much for this insightful class. There is something I still confused and want to ask about. It's about why is this reaction can occur only in 60 degrees Celsius, sir? Oh, yeah.
Right. So it is important to control the temperature of the reaction. Yes, it is really important. So let's talk about reactions that are done at room temperature. If you do this reaction at room temperature, you will not get products. If you do this reaction at 60 degrees, this is the optimum temperature for this reaction. If you do the reaction at 100 degrees, you will get a black mixture and the yield is very, very low. Black mixture is indicating decomposition of the product. At this temperature, your carbohydrate will decompose. All right, we are not able to obtain any product. Everything goes to a black mass. If you check the NMR, you will not get nothing. There's no signals that you can relate to the starting material, and there are no signals that you can relate to the product. And that's why we say it's a decomposition of product. All right. Now let's go back to we know that at 60 degrees, this is the optimum reaction. You know that, Ahmed, for materials to react, you need to have an activation energy. You need to have the right activation energy. Okay. So if you have A plus B, and you have an energy diagram here, you need to have an activation energy for A and B to react together. All right. If you mix them at room temperature, these don't react unless they are very, very reactive. But in our case, if we take the carbohydrate, we take the nitrile, we take the amine, all right, so, and C here. So if you bring these ones here and at room temperature, these things don't react at all because they don't possess the activation energy, the right energy to react together, all right? We don't have that. So we need to heat and give them energy so that they are able to react together. Clear, Ahmad?
Okay, sir. Understandable.
Thank
Thank you very much, sir.
Thank you. Balkia?
Hello, sir. I just wanna ask some question. One question. I just wanna ask for the reaction optimization. There is a 12 reaction from the glucose in the beginning your explanation, I just curious why there are two products and there is a ratio where the products one have 100% ratio. I just curious what is the difference of the 100% ratio and 89% ratio? What is the difference of the acetic acid? And what is the difference for the yield of this reaction? Sorry.
Right. So the difference here, the differences in the yields, what we get here, Ahmad, is because of the sequence we use. There are a few things that here we need to explain. All right. You can control the sequence based on the yield. Sorry, you can control the yield or the ratio based on the sequence. Again, you can control the ratio based on the sequence and also based on the catalyst. Based on the catalyst. If you look at this sequence here, this is zinc chloride. This is, so let's look at this sequence here, number 4. Zinc chloride, paratoluene sulfonic acid, and formic acid. So all of these 4 and 5, they give you 100% of 1A. Remember that zinc chloride is a Lewis acid. Paratoluene sulfonic acid is also an acid. Formic acid is also an acid. But formic acid gives you a mixture. This is, I think this is because formic acid is a weak acid. All right? Although you are using this reaction and sequence 1 under sequence 1, because it's a weak acid, we get mixtures of the products. So if you look at camphor sulfonic acid, we don't have any product. That's because it's a very, very weak acid. Now, if you look at 8, all right, this is a triethylamine. Triethylamine is a base. It gives us 1A dash completely. If you look at 9, it's also a base. It gives us 1A dash completely, right? Selectivity, very high selectivity, 100% selectivity. That means if you really look at all of these, which means the following: bases prefer to give us 1A dash. Acids prefer to give us 1A. However, if the acid is weak or if the acid is very, very weak, then we either get mixture of the product or no product. This is how you look at it. All right? And that is based on how these acids and bases activate the starting material, as we explained in the mechanism. Is this clear?
Okay. Thank you, sir. This is clear. Thank you for explanation. Thank you, sir.
Good, good. So, but yeah, this is also, there's one thing that I want to explain to you here also here. So if you look at entry 2 and 3, I am using 2 different sequences here, and I'm obtaining here either 1A or 1B. So this tells us that you can control the selectivity based on different factors, based on the sequence and based on what type of catalyst you use. All right? Because here we are using the same catalyst, but the sequence is different. And based on the sequence, you either get 1A or 1A dash. So this is what we can conclude is based really on the sequence or based on your type of base that you use. All right. It is important to choose the right kind of condition to obtain the product you want. I can see Diana.
Hello, sir. I want to ask you a question. There, in this table, there's no data of temperature as a condition affecting the reaction. If we edit the effect of various kind of temperature, will it affect the reaction time? Thank you, sir.
So here, the reaction, there's no data about the reaction time. So the optimum reaction temperature, not time, temperature is 60 degrees. Yes, definitely. So Diana, we chose this temperature based on our experience. I think what we found that the optimum reaction temperature is between 60 degrees and 80 degrees. This is the optimum reaction time. So we have not shown you here different reaction temperature. It's just we want to minimize the table that we have here. So this is basically the optimum table that we wanted to show you. But yes, I think this is the optimum temperature. Higher temperature will lead to a little bit of decomposition of product in this case. Yep. If you compare this reaction with the previous reaction, what do you notice? So let's look at this reaction here. So what you notice here, this takes 6 hours, right, to obtain this type of substituents. But if you look at this reaction here, this reaction takes place in just 3 hours. It means that this reaction is very, very quick in comparison to the other reaction. This is true because this material here, this nitrile here, is very reactive nitrile, is more reactive than the other nitrile. Yes. So we didn't we didn't want to show you the effect of temperature because this is the optimum one.
Oh, okay, sir. Thank you.
Good. Muhammad?
Okay, sir. Excuse me, sir. Can I still ask about page 36?
Of course you can.
I want to ask you about the entry number 8. It looks like the temperature is 80 Celsius. It's different from the others that has 60 Celsius. I want to ask you, I'm a little bit curious about how it happened. And then I want to ask you, what if we change the solvent to ethanol, and is it related to the boiling point of the ethanol itself? Thanks.
Okay, so let me answer you for the second question. So if you look at entry 10, we are using the same catalyst, we're using the same number of equivalent, we're using the same condition, and all we did is we changed the solvent to ethanol. All right, so we change from DMF to ethanol, and you're right, this makes logic. It is important to try to play with the solvent. The DMF is a high boiling point solvent, and it's very difficult to remove from the reaction. Ethanol is a very common solvent in the pharmaceutical industry and is also easy to remove. All right, it doesn't require a lot of heat, a lot of energy to remove. All right, so yes, we have tried what you said, and it's shown to you here in entry 10. Regarding your first question, which is 80 degrees and 60 degrees, where did 80 degrees come from? Look, 80 degrees come from the reaction. It comes from this table here. All right. So in the beginning, when you are doing reaction, you just really don't know what is the temperature that you have to play with. So what you do, you take a wide temperature range, maybe room temperature, maybe 50 degrees, maybe 100 degrees. All right. This is a wide range of temperature. And then you observe your reaction, you observe how much yield you get. And then you start to, increase or decrease the temperature based on reaction time and based on the temperature. All right. So there's a lot of factors that they play, not just the temperature, also the reaction time. But however, what we want to obtain is something that is really high yielding and a clean product. Clean product is very important. We know that if you use higher temperature, carbohydrate will decompose. 80 degrees is fine from our experience. But then when we are using 80 degrees, okay, this is something that's good, but can I decrease it more? That is the question. So you have to start from somewhere. We started from 80. Okay, why did we start from 80? It is based on our experience in the first section of the work. All right, that's why we started 80. And as you can see, we decreased the temperature to 60 degrees. Now, can the reaction happen at 50 degrees? Yes, the reaction can happen at 50 degrees, but instead of 6 hours, you probably need 10 hours or you need 12 hours. However, if you extend the reaction time, you will have more decomposition of product. In other words, your temperature, your reaction time, you have to have a compromise between these two so that your reaction time is not so long and your decomposition of product is not so much. This is the compromise that you need to have. Am I clear, Muhammad?
Yeah, sir, clear. Thank you very much.
Do you have any more questions, Muhammad?
Maybe we want to make sure. So it's based on experiment. Okay.
That's correct. It's based on experiment. Yes.
Okay. Then that's all, sir. Thank you.
Yes, I can tell you that we have done reaction at 100 degrees. I can tell you that we have done reaction at 40 degrees. But so in a seminar like this, we are not going to put all the reaction temperature, right? Yeah, but for your case, for your undergraduate, of course you have to try a different temperature. This is really important. We didn't know that this reaction is very optimum at 60 degrees. We don't know. We have to try.
Thank you, sir.
Okay, very good. Next question is from Nurli Rahma.
Okay, hello, sir. First of all, thank you for the lesson. I want to ask from the second section. Can we go to the second section?
Yep.
Uh,
Which slide you like to?
Next slide.
Tell me where to stop.
Okay, next slide again. Oh, no. Yeah, the previous slide, yes. Okay, so I want to ask, if we didn't use the catalyst, can we still have the furan or pyrrole product? As we can see, there is a catalyst that create no product, and how long the time difference between if we use the catalyst and no catalyst?
Okay, if you use no catalyst, you will not get products at all. So this work, I have not showed you these results, but if you attended my lecture last week, I have some entries where I used no catalyst, and I showed you there is no product. So if you don't use a catalyst, you will not get the product. It's important to use a catalyst to have the products. What was your other question?
The other question is if we can use no catalyst, but we cannot use the no catalyst, yeah.
Right. So no catalyst, no product. In fact, you will see that here. I'm saying here. So I'm saying here, which one here? This one here. Camphor sulfonic acid. I'm having a catalyst here, but this catalyst here is a very weak acid, and it didn't give us any product. So no product here. Yeah. So although sometimes you are using acid, the strength of the acid is very important in order to obtain the right product. Yeah. This is very important. I also can bring your attention to entry number 11. Yes, entry number 11. I'm using acetic acid, but here the solvent is not the right solvent. I'm using water. All right. And also here I have no product at all. Why? This is because my amine and my nitrile, they don't mix with water. All right. So this reaction doesn't proceed because these 2 and 3, they don't mix with water. Only glucose is soluble in water. The other 2 are not soluble in water. Therefore, there's no reaction.
Okay, so the catalyst is not only to speed up the reaction, but also to determine the reaction, yeah?
That's right. That's right. So the catalyst is to catalyze the reaction. Yeah. It first of all, it has to work. It has to catalyze before it speeds up the reaction.
Okay, thank you for the answer.
Thank you. Do we have more questions?
Marcia.
Marcia, Alia.
Okay, sir. So I want to know about something like when you already explained to us in the reaction, you use catalysts, like many catalysts that we use for the reaction, right? So my question is, when we use catalyst, is there any specific characteristic or reason for the catalyst that we can use for the reactions there?
Right. So this is a very good question. So what type of catalyst we are going to use? So in order for us to decide, I want to have something that, first of all, something that catalyzes the reaction, something that is cheap, something that is recyclable, if I can have it as recyclable, and something that is simple. All right. If you look at my catalyst, I'm using acetic acid. Acetic acid is, I mean, you cannot get cheaper than the acetic acid. It's very, very, very cheap. All right. And formic acid is also very cheap catalyst. Triethylamine is also very cheap catalyst, right? So the cost of the catalyst is very important, and the efficiency of the catalyst is very important. How efficient is the catalyst? Toxicity of the catalyst is also important. I don't want to use catalysts that have metals, because if you are doing this reaction for pharmaceutical industry, you will have a trace amount of the metals left in the product, and the industry doesn't want to have a trace metals. So I don't prefer to have catalysts that have metals. No, acetic acid is a liquid. I can easily filter that from my product. I can easily remove it. All right. I use zinc chloride. I don't prefer to use zinc chloride over acetic acid. However, because here I'm just examining and screening different types of acid catalysts. Here, pyrotoluene sulfonic acid, this is more expensive than acetic acid. All right. So I think you have the understanding that our choice of the acid, first of all, it has to work. Then it has to give us very high selectivity, very high yield. And then it has to be cheap, not toxic. A purification has to be good. Recyclability has to be very important. All right. Now, what again, I'm using here different acids because these have different strength. Yeah. The acid strength maybe affect the reaction time or the reaction yield or the reaction selectivity. So that's why I have to use different types of acids. All right. Is the answer clear to you?
Okay, sir. Thank you for the explanation.
Okay. Olia?
Olia.
Okay, thank you for the chance, and thank you also for the explanation before. And actually, you have explained in previous question that without catalyst we couldn't get the product. But sir, I'm quite curious about, is it possible is it still possible for us, perhaps in the future, that we want to develop a non-catalyst reaction by giving a certain treatment, maybe?
I think you need for these reactions to have catalyst. So Olia, the reaction, the catalyst is important. Why is the catalyst is important? Because these steps, right? These steps need to undergo based on removing water, based on activating. For example, here I'm using acetic acid. Why am I using acetic acid? So in the beginning, acetic acid react with this. So, you know, there is lone pair of electrons here and here. So this react with the proton, and this reaction give us this product. Oxygen here, and this is positive charge. The reason, so it's really important to understand this point that you mentioned. So this acid reacts, so this is acid-base reaction, and here is the product. Now, it is very important for us to add the acid. Why? Because when we add the acid, this carbon here becomes very electropositive. This charge here, this oxygen here, it has a positive charge. Now it is electron deficient. Because it's electron deficient, it pulls electron from this carbon. And if it pulls electron, this becomes very electropositive. It becomes very electrophilic. And I can show you the resonance structure. So if we push electrons here, then what we have is this oxygen here. When you push electrons here, you neutralize the positive charge, and this becomes positive. Now, this is very good substrate for the nucleophile. You can see here, the nucleophile to react on the carbon. So my nucleophile here, which is NH2, react here. If I don't have this acid as a catalyst, the reaction between the nitrogen here, nucleophile, and this carbon is either doesn't happen or very, very slow. That's why a catalyst is generally needed for these reactions. All right? Now, sometimes I'm able to supplement the catalyst with an increase in temperature. All right, sometimes you can just do reaction on higher temperature, you activate the compounds, and they react together. Is the answer clear?
Yes, it's quite clear for me. Well, thank you for the answer.
Thank you. Does anybody have any question? If you don't have a question, I have a question.
Yeah.
I don't know if Dr. Bayo want me to give you the question or no, but yes, I'll be glad to answer more questions. I think if you have questions, I can answer. This is good.
Yeah, maybe please introduce your question so
okay,
the student can learn after this meeting.
All right. Yes. Here is the question. This is what I want you to make. Can you make this one based on the chemistry that I taught? So we are going to be something called forward looking. So let me help you. Does anybody before I help you, does anybody have any clue? Does anybody have any idea? Okay, here is what I want to help you with. This is one section. Okay, this is one section. This is another section. And this is another section. So I think you know where this section comes from. So you are very familiar. You should know where this section comes from. Do you know? Do you guys know? Somebody answer. Do you know?
Okay, anybody want to answer? Because we have a bonus.
Yes. Muhammad, do you know how? I think we have so many Muhammad here. So one of you, Muhammad. Anybody knows? Come on, we know, right? Okay.
Excuse me, sir.
Yes.
Isn't this one you have already shown us in the previous work?
No.
I think it's very similar to the one in your first presentation in your unpublished work, where you use I forgot what the reagent is called, what the other reagent is called. But yes, first you use aniline and then you use phenyl. What's this?
So you know how to solve it, Muhammad?
Yes, I'm not so sure about the chemical names. It's
okay.
been.
So what is the chemical name? You don't have to give me the chemical name. So what is the structure?
The structure, first of all, you have already drawn the aniline. So
that's right.
First is aniline. And then the other reagent is two cyclohexane rings with ketone, and then another hydroxyl next to the ketone, but they're opposite of each other and mirrored.
So this is the one here?
Yes, and then I was talking about the hexagonal structure.
Okay. So this one here comes from where?
Which one, sir? Sorry, the top one?
So this one comes from here, right?
Yes, it just basically replaces the methyl with a phenyl group.
And this one comes from here, right?
Yes.
So what is this one come from?
With a phenyl group.
Sorry?
The bottom part replaces, in the first presentation, it's a hydrogen group, but then in this one is replaced with a phenyl group. So a phenylamine or aniline instead of.
Yes, so we agree that this one is here.
Yes.
This is correct, and this is correct. I'm asking, where does this one come from?
From what do you call it? Hemiketal, I believe.
So this is the question we are asking.
Cyclic compound.
Yes, it's a cyclic. Hold on, I can actually just search what the chemical. Yes, from ChemDraw. The structure's name is. Yes, this looks correct. Name is called. What is this called?
Okay, so what do you have in the what do you have in your structure?
Benzoacetyl.
Okay, Muhammad, you have a camera?
Oh, I have a camera, but I do it on my laptop, not on my not on paper.
You draw it. You draw. Do you have Do you have a paper to draw it? If you don't have a paper, you draw it on your hand and show us.
Okay. Okay.
How is that?
Okay. Okay. Yes, sir.
How is that?
Yes. 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 Oh, actually, I have a paper.
Okay, you draw it and show us, please. If it is convenient. If it's not convenient, it's okay.
Oh, it's okay, sir. It's okay. Yes. Listen to that. Yes, that is correct. Oh, oh, my time's running out. Sorry if it's a bit okay. Sorry. Oh, I have to.
Yeah.
I have to remove my virtual background first. Where is it? Actually, no. Wait. Can you? Oh no, no, it just doesn't work. Virtual background, none. Okay, there you go. Can you see, sir? Sorry. I think it's mirrored on.
Okay. All right.
Yeah.
Okay, I know what you are trying.
Okay. Because I saw this on your last presentation where the
you have a good memory. So
yeah,
but what I wanted you guys to think is the following. All right, let me explain it to you. So if you look at these structures, right? If you look at these compounds, everything what we have here, what we had here, what do we have here? Look.
Oh, that's an yeah. That was what I was trying to say. There is a hydroxyl alpha towards the aldehyde.
Yeah, hydroxyaldehyde. Yeah,
Aldehyde.
Hydroxyaldehyde. So for all of you, what do we have here? We have this kind of arrangement. All right. If you notice that these groups basically don't involve in the reaction. What is involved in the reaction is this. Right? This is what is involved in the reaction. This is carbon and carbonyl group and hydroxy. Therefore, by right, if I have this kind of arrangement, if I have this kind of arrangement, then this should react with this one and this one to give me pyrrole. Am I correct? Now, if you look at this one here, you will find that this is a cyclic structure. Therefore, what you would think is that, hey, this has to be cyclic structure. And the cyclic structure is this one here. Oh, why is that? And what I have here, sorry, I don't know if I can. Yeah. So please neglect this one. Yeah, neglect all of it. So what I have here, I have a carbonyl group and I have an OH group. This is exactly the same arrangement that we have in case of carbohydrates, right? This is the same arrangement we have. We have an OH group here, and we have an aldehyde group here, or a ketone. So I have this, I have this. The relationship is 1, 2, 1, 2. So if I take this structure, and I take this one, and I take this one, then I will get this product. So suppose that you want to have a methyl group here. All you need is to start with something that has this group here, methyl group here, right? Suppose you want to have another ring here. Then you start with something that has another ring here. What I want to say is that the scope here is very, very unlimited. You can change this section as much as you want. So for us, we recognize that, okay, we have this arrangement here, and we need to change the arrangement. If we make a cyclic structure, then this gives us another dimension to our chemistry. And therefore, next week, I am going to teach you, I'm going to teach you reactions to form this type of ring, and also reaction in which I'm not using carbohydrate, but I am using this type of hydroxyketone. So next week, we will learn two things. This hydroxyketone to form these indoles, and this type of hydroxyketone to form this type of indoles, these types of pyrroles. Also, I will tell you next week that when I get this pyrrole, I can do another step of dehydration. I have an aromatic ring here. If my ring is aromatic, this now is called indole. So we can make indoles from this type of chemistry that I'm going to show you. So next week, I'm going to explain to you reaction of this one and reaction of this one. Does anybody have any question? Any last question? So this is how our chemistry is developed, and this is how we think to develop the chemistry that we already have. Yeah. Any questions before we close this? Any questions?
Okay.
All right.
One more question, maybe?
Yes, one more question. One more question.
Okay, maybe no questions.
All right. So can I maybe what I can do? Can I ask you to do what? So for all the students, can somebody think about different chemistry that we can use to obtain different type of compounds? So building on the chemistry, building on what I told you here, the concept here is to use hydroxyketone and do the reaction. Can somebody maybe suggest a new kind of chemistry or a new kind of compound, a new kind of a structure for us to see if you, for example, if you want to work on this chemistry, if you want to develop this chemistry, what will you do? What is the new chemistry you will do? This is my question. Can all the groups please try to answer this question? So the question is this: if you want to develop this chemistry, if you are a research student, a PhD student, and you want to develop this chemistry, what kind of chemistry you will do? What kind of new structures you will prepare? Is the question clear? So maybe all the groups that Professor Bayo divided, maybe they can sit down together and answer this question. I'm looking for a new chemistry or new compounds that you can develop based on what I taught you. So next week is going to be really exciting.
Okay, everyone, please discuss with your group member, and next week, please prepare for the answer. Maybe you can write down in your paper and then submit it. because maybe students need time to think about it.
Yes, they need a lot of time. When is our next lecture?
This Wednesday at 8 a.m. to 10.
Oh, okay, this Wednesday. Yes. Okay, I think they have some time. Today is Monday, so.
Okay, because of the time limitation, so thank you very much, Prof. Zaher, for your very interesting and comprehensive lecture.
Thank you so much. Thank you.
Before we close this today's lecture series, we have a photo session. We have a photo session. So, if possible, please open your kamera. So, Mbak Safira atau Mbak Jenia bisa memimpin apa atau screenshot ya.
Baik, Pak. Yeah, for all the participants, please turn on your camera. Now we'll start to screenshot for the session. Have you all turn on the camera? Okay, so there are many students who already turned on the camera, so please smile at the camera. 1, 2, 3, please. Okay, next page. 1, 2, 3. Okay, next page again. Yeah. Okay. I think that's all for the photo session, Bapak Dr. Bayu.
Ya, terima
Thank you
kasih.
very much.
Ya, terima kasih Mbak.
Terima kasih
Oke,
banyak, Pak.
Professor Zaher and ladies and gentlemen, all students, finally we come to the end of the lecture session. So I would like to say thanks again for all participants for your very active discussion with our professor. So hope the presentation or material will be beneficial for everyone. Thank you also for Prof. Zaher for your knowledge, and happy Ramadan Karim, and have a wonderful the fasting month.
Thank you, Dr.
Okay.
Bay. Thank you. And
Yeah,
thank you
we
all
close this session. Thanks so much. Assalamualaikum warahmatullahi wabarakatuh. Good evening.
Assalamualaikum.
Yeah.